Einstein's theory of general relativity is one of the fundamental pillars of modern physics. Its elegant accuracy means that it's still the best theory cosmologists have to understand the force of gravity. But how and why are its predictions true? Building on our knowledge of special relativity from the previous two videos, this is how to derive Einstein's greatest breakthrough. For general relativity, we must first expand on the first postulate of special relativity, to enable it to include accelerating frames. Einstein did this with something called the equivalence principle. Imagine men in two lifts, one in a tall lift shaft on Earth, and one in a spaceship floating weightlessly in deep space. The cable of the first lift breaks, putting it into freefall and accelerating towards the ground. Now, both men are floating freely inside the lifts in the same way. Therefore, Einstein assumed that gravitational freefall and true weightlessness were equivalent. Since you cannot feel its effect accelerating you, he wondered whether gravity was even a force at all. Now the first lift hits the ground, and at the same time, the spaceship turns on its engines and accelerates upwards. Now both men fall to the floor of their lifts, and once again the lifts cannot be distinguished. This shows that the effects of acceleration can also be produced by gravity, and vice versa. These two thought experiments led Einstein to classify gravity as a so-called fictitious force, along with the inertial force that pushes you back in an accelerating car, or the centrifugal force that throws you towards the outside of a roller coaster loop. Fictitious forces are not caused by two objects interacting, but are rather a consequence of being accelerated. Let's go back to our free-falling lift, accelerating under the Earth's gravity. It passes two clocks on the side of the lift shaft. Since our observer is in an inertial frame moving relative to the clocks, the effect of time dilation applies, so the first clock ticks slower than it would do at rest. By the time it falls past the second clock, it is accelerated to a higher speed, so there is more time dilation, and the second clock ticks even slower than the first. We can use the equivalence principle to show that this means that time will run slower lower down in the gravitational field. This is gravitational time dilation, an effect demonstrated when atomic clocks transported to the top of mountains were found to run faster than those kept at sea level. Einstein now had to work out how the mass of objects could produce acceleration. The effect of gravitational time dilation means that large masses, capable of producing a gravitational field around them, distort the space and time inside their gravitational field, just like a heavy ball placed on a sheet of rubber stretches it out around the ball. However, note that it is not as simple as this. There can be no gravity pulling the objects towards the lowest point on the sheet. This is in fact what we're trying to create. So, how does warped space actually produce the effect of gravity? The best way to think about this is with a distance time graph. This particular graph is that of a stationary object in non-distorted space. It traces out a horizontal line. As time passes, its position remains unchanged. Let's say it stays 6 meters away from some arbitrary point. Now we'll bring in a planet with a mass large enough to cause distortions. With its space-time axes warped, our graph now looks something like this. As before, the object follows the same straight line, but if we read off the displacement values, they are changing. The object is now moving, not just with a constant velocity, but it's accelerating towards the planet. This acceleration is what we call gravity. Notice that there is nothing actually pulling on the object. It's still following a straight path through spacetime, according to Newton's first law. The object just appears to accelerate because spacetime is not flat. Describing curvature of a 4D entity is difficult, but a useful analogy is the geometry of curved 2D surfaces. We are most familiar with flat plane or Euclidean geometry, where angles in a triangle add up to 180 degrees, and so on. However, this is not the only type of geometry. We can curve our flat surface into a sphere, and now we can construct a triangle with 2 or even 3 right angles. Or we can curve it the other way to form a hyperbolic plane, a strange land where triangles can have 3 30-degree angles. Bernhard Riemann used some rather tricky maths to generalize this to any number of dimensions, but the basic idea is the same. On a sphere, a straight line, the shortest distance between 2 points, is a section of a great circle which is actually curved. Similarly, the curved orbits followed by objects in gravitational fields are equivalent to straight lines in the curved geometry of spacetime. Remember, the straight line on the graph still produced acceleration. Einstein used Riemann's theory to develop an equation to show how gravity formed. Here it is. G mu nu equals 8 pi g over c to the power of 4 times t mu nu. The g mu nu represents the curvature of spacetime, and the t mu nu represents the distribution of matter in the universe. The bit in the middle is constant, so we can take it out and we are left with this beautiful relationship. Curvature is proportional to matter distribution. The equation, and general relativity as a whole, was summarized in this way by physicist John Wheeler. Spacetime tells matter how to move, matter tells spacetime how to curve. Einstein's equation represents half of modern physics, and thus is where we shall leave relativity for now. Next stop, the weird world of quantum mechanics. See you there.